Good morning, everyone. Hope everyone is well. So, Physics 1, Part 2. Last lesson, we started looking at... oh, did I turn this off? There we go. Last lesson, we started looking at different types of energy transfers. Morning, Tanishka. So we looked at energy stores, and we looked at the differences between stores and transfer methods. We said that actually one of the most important things in physics, morning Amy, is when we're looking at the conservation of energy, we said that actually what we're looking at is that energy cannot be made or destroyed. We can only transfer it from one storage area into another storage area, and it can't stop between those storage. So whenever we look at energy transfers, what we're trying to work out is what stores is the energy starting off in, what is it ending up in, and there is often more than one store. Generally speaking, we start looking at efficiency and places where energy might be lost. There's probably going to be multiple stores at the end of it where the energy is going to be end up. Although usually when you sort of work on the final end result, it's often thermal. But that's sort of the biggest challenge for us, is what are the stores of energy that's involved in particular transfers. The transfer method then is just the route the energy is taking to go from one store into the next. So we said that actually light itself is not an energy store because we can't store light. But what we can do is light will be the transfer method. So for instance, if we had a torch, we've probably got chemical energy in the torch. That chemical energy is being transferred into electrical energy and then into light energy. But those are just transfer methods because ultimately it's ending up as thermal. So let's carry on and look at some examples specifically. We're looking at conduction, convection and radiation. And I think that's where I'm going to start off today. We're going to have a look at some sort of specific examples. I've got some pictures taken from past exam questions, so have a look at those as well. And then we're going to have a look at some calculations, particularly around specific heat capacity and how we can sort of do some of those and how we can rearrange some of the questions. So yeah, let's make a start. So this is one type of hot water tank that we might see in our homes. Now, in a lot of homes, we might have a boiler which will be heating up the hot water tank before it gets to here. But some houses, I know my friend down in sort of Chichester way, they don't actually have a boiler for hot water. They've got everything's electric in their house. So they will have a system very, very similar to this one. And again, this is quite common in America. So what we have, and let me just change colour so I can highlight some of the points on this one. We've got insulation, and we'll look at why that's relevant in a moment. And if I was doing an exam question, it's trying to look at, I suppose, where the marks are going to be in this one, and what sort of things might they be asking for. And bearing in mind, I've not put any of the question in here. We've got hot water leaving, we've got cold water going in. We've got electric immersion heater. Immersion just means it's inside the heater. So it doesn't mean, it's not important for any other reason apart from the fact it's inside. And that's our heater. Now, there's a couple of sort of design features here. If you notice, the cold water is coming in the bottom rather than the top. And notice that the immersion heater is actually sort of placed near the bottom of the tank. Now, if you think about what we were talking about last time, we should be able to start trying to work out why those design features have been put in the way they have. So the immersion heater itself will literally be a high resistance piece of metal. The electrical current is going to go in and it's going to cause that metal to heat up. So we're actually going to have a conduction happening in that metal. And we should be able to link this back to kinetic theory. So as the electricity is going in, it is going to be transferring energy to the metal in that heater. That's going to cause the atoms in the heater to start vibrating. And as they vibrate, they're going to hit the particles next to them to make them vibrate faster as well. And as they vibrate faster, that means they've gained energy, so they're also getting hotter as well. So we've got that sort of link between the movement of the particles and the energy they've got coming in. So that's sort of the conduction. Now, the next thing is why we sort of placed it near the bottom. Remember, heat itself does not rise, but hot particles do. And that's really important. So what's going to happen is as these cold water particles touch the rod, and we could do this as a series of bullet points if we wanted to do it as a long answer question, but as these cold water particles touch the rod, the vibrating particles in the rod are going to hit those cold particles and they're going to transfer energy to them. That's going to make the cold water particles basically gain energy and start moving faster, so they're going to bounce off each other more. So as they bounce off each other more, they're going to get further apart, and that means they have become less dense. So if we're going to bring in density here as well, we've got the least dense and we've got the most dense down here. And what I'd be expecting to see with this in a diagram or in a question is being able to link together the density and the energy and explaining why the lower energy means you've got more dense particles. What we can see then is that because they're least dense, they're going to rise up, which is why we're going to get the hot water leaving through the top of the tank. Now, what we don't want to do is spend our hard-earned money heating up this water and then just have it being wasted. So what we do is we put some insulation around the tank. And a lot of the time, this will be usually foam. And it's like a hard foam. But it might also have sort of insulation material as well. So it might also have some fabric. And all of these are designed to trap air. So this is the same idea as the reason that we wear clothing in the winter to stay warm. It's also the reason, if you remember last session on Monday, when I spoke about the insulation in the walls of your house, and we said actually what happens is if we didn't have it there, as the air particles between the two walls in the house heated up, it would rise to the top, leaving colder air at the bottom. And as you get this convection current going, the bigger the convection current, the bigger the heat gradient. Because what we end up with is if we can keep cold air around the outside and hot air and hot water inside, as long as we've got this temperature difference, we're going to be getting heat moving from inside to outside. So if we can actually trap this air and stop it leaving, we're actually going to be keeping hot air around the outside as well. Morning, Chris. We're going to be keeping hot air around the outside as well, which means we're going to be reducing the temperature difference, which means we're going to reduce the rate that heat is lost out of that tank. And that's pretty much, whenever we're looking at trying to stay warm, that's what we're trying to do. We're trying to trap a layer of air, which we are going to heat up, but then because it stays where it is and doesn't get lost, we reduce the energy transfer. If you look at creatures like polar bears themselves, they look white and fluffy, and they are fluffy, but what you actually end up with is black skin on the polar bear. The black skin is to absorb as much heat as it can, and the fur itself, whilst it looks white, is actually clear, and it's clear to allow as much light through to the skin as possible. And the hairs are hollow, so because they're hollow, that means they've got air inside them, and all of this adds up to increase the insulation properties of the polar bear. And when you actually look at where they live, even though it can be -40 and below, they can't actually run for very long because they overheat, because the insulation qualities of their fur is so good that they just don't lose that much heat. So they can't actually run for very far when they're trapping prey or chasing prey. So all of these things are linked back to those sort of fundamental ideas of conduction, convection, and radiation, and the movement of particles, so kinetic theory. So as I said last time, it's really, really important that you get a very good understanding of what this idea of kinetic theory is and how we can use our knowledge of it to keep ourselves warm or to cool ourselves down in the summer. So let's look at another example of heat transfers. Or sorry, heat transfer, energy transfers. Let's go with a drone for the moment. Quite like drones. I've just ordered loads of parts to actually build my own at the moment. Something I want to be doing in school is actually I want to set up a club. So I want to get some of you guys actually designing and printing them on 3D printers and then actually building them. So I quite like the idea of what's going on here, but it's worth having a look at the sort of energy transfers that's going on. Now, the first thing we want to identify is, let's assume to start with that we've got, and let's put another picture in here. So let's assume that my drone is on the ground. Okay, so we've got it on the ground, and it's not actually fired up at all at this moment in time. So the first thing we want to do is work out what energy transfers we've got, or what energy stores we've got. So whilst it's on the ground, it's all going to be chemical. So it's not moving, it's not going anywhere. So any energy that this drone would have would be in the battery. So we've got a chemical store of energy. Now, as I turn this drone on, what's going to happen is this chemical energy is going to be turned into kinetic. And the pathway for this is going to be electrical. Now, we are also going to have a thermal store. Because as those motors spin up, there will be a certain amount of friction involved. We're also going to be a small amount of heat going to be generated in the wires. So we're going to get some thermal energy as well. So I've actually got two stores of energy at the moment. Now, we could actually argue that we can hear it. So we've got sound. Now, technically, sound is just the movement of particles. So although, yes, we can sort of think of it in terms of energy, what we're really doing with sound is we're making those particles vibrate. So in other words, we're actually eventually ending up as thermal. So I don't need to put it down as a separate energy source at the moment, or a separate energy type at the moment, because again, it is just the vibration of particles, which is why there's no sound in a vacuum like space. So we've got this kinetic energy, and actually, if I increase the kinetic energy, and a slight link here to one of the later physics topics, if I increase the kinetic energy, those blades are going to be pushing air downwards. So that's going to create lift. So if the lift is actually greater than gravity, and I've deliberately done these arrows different sizes, if my lift is greater than gravity, then actually my drone is going to go up. If it's not, I've still got the energy transfer because I'm still pushing air out of the way, which is still creating sort of kinetic energy in that case, because we're still pushing those air particles out of the way. Now, what's going to happen then is my drone is going to go up into the sky. So as this happens, what we're now creating, did I just say that? Need a slap. Can't create energy. What we're now doing is transferring the kinetic energy into gravitational potential. Okay? Ignore the fact I just said the word creating. If this was done and it wasn't live, I'd be going back and rapidly editing that. But no, we're transferring the kinetic energy into gravitational potential. And the higher the drone goes, the greater that gravitational potential energy is going to get. Eventually, we're going to get to the stage either where we can't go any higher, or we just don't want it to go any higher. In which case, we could just shut off all of the power. So we could shut off all of the power to the blades, and then the gravitational potential energy that we've got would be converted back into kinetic energy. And theoretically, if we ignored air resistance completely, and I know we can't do that on Earth, but let's assume we could, then the maximum kinetic energy this drone could achieve would be equal to the gravitational potential energy it's got. And if you remember back from last week, gravitational potential energy equals the mass times the height times gravity, or it equals the weight times the height. So if we knew how high the drone went and we knew the mass of the drone, we could work out how much gravitational potential energy it's got in joules. So that's just sort of an example that we could do. We're sort of having to look through. We've got working out what store we've started, and then we're working out those stores of energy as we're working our way through. So if there's any sort of confusion with any of that, let me know. But hopefully that does make sense. And it's one of those things, the more you practice, the easier it gets. And you can do this with anything. Literally just design or just think up anything that's either working or moving that you want to plug in, or any machine, and then think through. You can draw a picture, you can do flow diagrams, and you can work this out at home and just practice trying to identify those energy stores and the transfer methods. And if you want to take a picture of it and then send them through to me to have a look at, that's absolutely fine. but it's worth just practicing identifying them. Right, just do one more. And I'm going to have a look at, I think we'll do, I say one more, I'm going to do two more. Let's do this one. So I said last time that I want to try and do more exam questions with the physics. Tanisha, we start with the chemical energy. Yeah, whilst the drone is moving, or the propellers are moving, we've got kinetic energy. And then as the drone goes up, the kinetic energy is going to be converting into gravitational potential. You'll see it again with the tennis ball here, actually. So if we were to look at the energy transfers happening in this case, in actual fact, the energy that we're starting off with is going to be chemical again. So it's chemical energy because we've got that energy in our muscles. So the chemical energy comes from the food that we eat, and then our body stores that. In my case, probably stores a bit too much. But anyway, we're storing that chemical energy. As we throw that ball, it is being converted into kinetic energy. So we're throwing the ball upwards. So here we're going to have chemical. We've got kinetic energy as the ball is moving. And then at the very top, we've got our maximum gravitational potential energy. At this point, the ball has effectively stopped. Now that takes a bit of getting your head round, but if you think about it, the ball's going to go up and up and up and up and up and slow down. At some point near the peak, it's going to reach 0 meters per second, so it's effectively stopped. But straight away, it's going to start falling back down as gravity pulls it back down. So we're going to go back, or up to GPE. And then we're going to go back to kinetic. And what happens after that depends entirely whether we catch it, whether we let it bounce. But for the moment, we'll just go with that. So we've got chemical to gravitation, to kinetic, to gravitational potential, and then back to kinetic again. And if you notice down here, what we've actually got is some information that we can try and use. So I've got this bit here, which is the velocity. If those of you in year 10 should know the difference between velocity and speed. If you're in year 9, you will possibly have done this in Key Stage 3. The main difference is velocity is a vector measurement. So velocity will always have a speed, so a size or a magnitude, and it's going to have a direction as well. Think about the vector character in Despicable Me. When he's describing himself, it's because he's got magnitude and direction, and that's exactly what velocity is going to have. So in this case, we've got the speed upwards. So as it leaves his hand, it's going to accelerate almost instantaneously to 5 meters per second, and it's in an upward direction. And because I've got the upward direction on it, it's going to be a velocity, not a speed. I've then got this, which it tells me quite nicely is a mass. Now, straight away, I can do a calculation with this one. I can say, well, I've got kinetic energy is going to be half times my mass times my velocity squared. What I would always do when I'm doing maths calculations, I call it the 3 S's. We scribe, substitute, solve. Scribe just means we're writing out the formula. It takes a couple of seconds to write a formula out in this format. So don't be afraid just to quickly write it out. The number of times in class when students go, I can't do it, and what they haven't, they're trying to do everything in their head, and it just doesn't work for most people. Even myself, I've been doing this for years. I still like to write it out, substitute in, so that I can then go through and I can start seeing what's going on. So the first one is scribe. My second S is going to be substitute. So in this case, I'm going to substitute in the values. M is 0.058. It's got to be in kilograms, and luckily enough, they've already given it to me in kilograms. Generally speaking, they will give it to you in all sorts of different measurements, and you will be expected to make sure you convert it into kilograms before you do anything else. So I would be looking at these measurements before I actually start doing the 3S's, and I would get them into the units that's needed for the calculation I'm going to need. So I'm then going to multiply that by my velocity squared. So that's by 5 squared. So just to make my life easier, I'm going to do that first. Multiply by 25. So I've already done that bit. If I don't need to worry about the units too much, that's pretty much an acceleration. So I can then go through and I can type this into a calculator. So let's bring out my calculator, and I'm going to go 0.5 multiplied by 0.058 multiplied by 25. That gives me a value 0.725 joules. Remember, it's an energy, so I'm going to put joules in there. And it hasn't taken me very long to write this out, but I'm more guaranteed to get higher marks with this one. It also means if I type this into the calculator wrong here, and it's quite likely with some of these calculations, this will be a minimum of 2 marks. It's probably near a 3. I can't remember off the top of my head. But even if it's worth 2 marks, if I manage to type this into the calculator and get it wrong, because I've done this bit here, or this bit here, I'm guaranteed to get 1 mark for the question, even if I get the answer wrong, because they know it's just a calculator issue at that point. On that note, always have a calculator in the exam with you. You are allowed a calculator in all of the science exams. Make sure you have your own. Don't rely on the school. The ones that we buy in for students to use in schools generally be quite cheap because we need to buy them in bulk. And also, because you're not using them day in, day out, you don't get familiar with them. And the last thing you want in an exam is to have someone else's calculator that either doesn't work or that you're not familiar with, and waste those precious seconds in the exam having to figure out where the correct function is to do the maths problem that you're trying to achieve. Whereas if you buy your own now and you practice with it from now until the exam, you're going to know all of the functions, all of the features, and exactly how it's going to work. You're going to learn to work around any quirks it might have. So this is going to be the kinetic energy that the ball is going to have here. Remember, that is our kinetic energy, and as we throw it, that's going to convert into GPE. So what we can do with this one, let's just move that up. What we can do with this one is we can turn around and say, well, the maximum GPE, and this is a really, really common 1 mark question in the exam. I know because it's worth 1 mark that I'm not expecting to do a calculation. But what they'll often say is, ignoring air resistance, what's the maximum gravitational potential energy that we could achieve here? So in this case, our maximum gravitational potential is also going to be 0.725 joules. We can't make or destroy energy, so if we ignore air resistance, there's nowhere else for the energy to go. So that kinetic energy is being converted to gravitational potential as the ball's going up. So what we could do now is we can turn around and say gravitational potential equals the mass times height times gravity. Now, if I know that the GPE is 0.725, if I know that the mass is 0.058, I don't know anything about the height, but I know that gravity on Earth is 9.8, what I could do is work out the maximum potential height this ball will reach. So let's go ahead and do that. What I would do is I would multiply the 0.058 times the 9.8. So let me just go ahead and do that now on my calculator. So let's do that again. 0.058 multiplied by 9.8 equals 0.5684. I'm not rounding it at the moment, but I might do that later on. So I now need to rearrange this. So my height, if I divide both sides by 0.5684, I move it from this side to this side. I'm apologising if you're a maths teacher and you're looking at this going, no, you can't explain it like that. It's not how we do it at school. That's how I would do it. If I'm multiplying both sides by 0.5684, to move it from here to here, I'm going to divide both sides by the same thing. So we can work that out now. So if I we just type that into it again. 0.725 divided by 0.5684 gives me a maximum height of 1.27 meters. So I didn't actually have any of the question here. What I was doing is playing around with numbers and working out what the examiners could ask me. Obviously, if we had the full question there, I'd have gone through it. But what I wanted you to do is see how we can use effectively 2 bits of information in a question to get quite a few marks depending on what they want with this one. I started off going through kinetic energy. I used the formula. Notice for each of these I followed the 3 S's. I scribed the formula, so I copied the formula. I substituted in the values or the data, and then I went through and solved it. And actually from this information I worked out how high you could throw the ball to. Right. If any of that doesn't make sense or you want to slow it down, feel free. I mean, go back through. These videos will all be on the YouTube channel afterwards. If you've subscribed to it, or even if you just want to go back in to find the channel later on, absolutely fine. Go back through. If you want to slow it down and work through any of those stages, sometimes it's worth just seeing these things a few more times. Now, this was a question that came in. Let's do, yeah, this one. Now, again, we've got a few different bits of information on here that we need to think about what's going on before we rush in. It's very sort of quick and easy for people here to go, oh, it just looks complicated, there's too much information, I just can't get my head around it. So just take a minute to have a think about the information they've given you in this question and what's likely to be happening. Okay, so we know we've got a bungee cord, so our bungee is going to stretch. Now, as it stretches, we're going to be converting some of our energy into elastic potential. So we know somewhere down the line, down here, they're going to have elastic potential energy. Up here, they're going to have gravitational potential energy. And as they jump, somewhere around here, going down, they're going to end up with our store of kinetic energy. So the gravitational is going to be converted into kinetic, and then that kinetic is going to be converted into elastic potential as the bungee extends. And the length the bungee reaches will depend very much on how much gravitational potential they've got. But we'll have a look at that in a moment. So 20 meters, and I think this says somewhere else in the question somewhere, 20 meters was the length of the bungee. So this is the length we're going to have no elastic potential at all. So all of the energy transfers at this stage is going to be from kinetic potential, from gravitational potential into kinetic. Now, what I would do is they've given me gravity and they've given me the mass. And I know for a fact here, I've got a height. So I can work out the gravitational potential energy and the 3 S's, scribe, and substitute. So mass is 50, height is 20, gravitational is 9.8. I haven't had to do any thinking at that stage. All I've had to do is copy out a formula and write some things in, and I'm probably going to get some marks just for doing that. Now, I'm going to type this into my calculator. It's a science exam. It's not a maths exam. We can use the calculator for doing this. So 50 times 20 times 9.8 is 9,800 joules. Yeah, Tanishka, definitely. On a trampoline, it's exactly the same thing. When you jump up, your chemical energy in your body converts into into kinetic, which means you go up, and that then translates into gravitational potential. As you come down on a trampoline, your gravitational potential, we go through kinetic energy and into elastic. Because we're also using our legs still as well, we're then adding more of our chemical energy. So we're adding kinetic energy each time. So there's a lot of energy transfers going on a trampoline. So our maximum gravitational potential energy here is 9,800. So we know our little man up here has 9,800 joules of energy. That's going to be converted into kinetic energy. So the maximum kinetic energy this person could achieve, if I put max kinetic energy, also equals 9,800 joules of energy. And that's ignoring all of the other forces, air resistance and everything else that's acting on them. So we could plug this into our calculation to work out how fast they would be travelling when they reach this maximum kinetic energy. So let me have a quick look at that one then. So kinetic energy, same thing as before, half times mass times velocity squared. And a lot of this is theoretical. So 9,800 is my maximum kinetic energy, is half times my mass of 50 times velocity squared. Half times 25, sorry, half times 50 is 25. So what I could do now is divide both sides by 25 to move the 25 across to this side. So 9,800 divided by 25 equals velocity squared. So let's get a value for that. So that's 392. To work out the velocity then, this is because velocity is v, at the moment we've got v squared is 392. What I would need to do is square root both sides to work out v. Okay, because the opposite of squared. So let's just see if this is going to work. Oh, wrong one. .8. Okay, so we're 19.8 meters per second. That's quite quick. So he's now falling at 19.8 meters per second, or his theoretical maximum. Realistically, he probably won't reach that speed. If you think about over the 20 meters, that's the maximum speed he could reach, but he'll have the air particles hitting him as well. So he won't quite reach that. Although over a short distance, it's probably going to be far off. Now, that 9,800 would then be converted into elastic potential. So the 9,800 kinetic energy would start heading towards zero. The elastic potential would start increasing as the person was falling. If the exam question had given us the elastic potential of the bungee itself, we could theoretically work out how far he would fall, and we could confirm whether this 55 meters, or we could use this 55 meters to work out the elastic potential. So let me just show you that one quickly, and then I'll move on to something a little bit simpler, because we've got a lot of formulas going on. So if you remember the other day, the other formula that I said we had was our elastic potential energy is equal to half times my spring constant times my extension squared. Now, if I substitute in, again, just the values we've got, 9,800 is equal to half. I don't know my spring constant, but I do know that the bungee is going to extend by 55 meters. So 55 meters squared. So let's type that into a calculator. Let's see what 55 squared is. .55 times 55 equals 3,025. And I'm going to multiply that by a half to get rid of the half. So, I should have done that in my head. 1512.5 times K. So, let's have a quick look. I'm multiplying by 1,512. So, the opposite of that is to divide. So, 9,800 divided by 1512.5 equals K, which equals 6.5. So my spring constant would be 6.5. Right, if I've lost you any of that, do say. All I'm doing is playing around with the calculations I've been given, and I've been linking them together. These sorts of calculations, so going from, if I was to go from, say, the gravitational potential energy calculation to the velocity, that is going to be 5 or 6 marks in the exam because I needed 2 formulae. As soon as we go into 2 formulae, we have to start going then for 5 or 6 marks. Now, sometimes they'll talk you through and they'll take this through stage by stage. They'll get you to what's the formula for this, what's the formula for this, work out this, then work out that. Other times, they may just turn around and say, using the information given, calculate the maximum velocity or calculate the elastic potential value. That is a higher level question. It's worth quite a few more marks. But if you work through the way I have done and try and break it down into simple things, if you're looking at it and you think, I haven't got a clue where to start, what formulas do you know that would include these values? Now, to start with, realistically, the only formula we actually had was GPE. It's the only formula that links mass, height, and gravitational potential together. So let's just go ahead and work it out. I've now got an energy value, which means it opens up more questions that I could use. Because I could either use kinetic energy or I could use the elastic potential. It doesn't matter at that point. But that was the only one that I could use given the information given to me. Unfortunately, at GCSE, there isn't any way round learning the formulas. You just have to memorise them. Now, personally, the way that I memorise them is to use them and keep using them. If I don't use them for a while, I start to forget. So I have to go back through and revise myself. And that's as a teacher that's been doing this sort of 15 years. So, and that's not anything to do with me. It's just the fact that with the way the brain works, it's in there somewhere, but I've got to bring it to the front of my memory before I teach it. So I'll go through and I'll practice and I'll use it to make sure that I can remember it again. And once I can remember it, I can then use it. And that's just being normal. So likewise, if you're looking at this now and then you don't touch it for several more months, you're going to forget some of these formulae. There is a free app you can put on your phone called, I think it's 21 Equations. Hang on, let me have a look. 23 Equations. And it's free. It's on Apple and it's on Android as far as I'm aware. So, I mean, I've got it on Android. So go through and put it on your phones. And what you can then do is either get it to do random calculations, or if there's one calculation that you're struggling with, you can select that calculation and they'll give you questions to practice using it, practice rearranging it and doing things with it. So it's well worth putting something like that on your phone. Or if there's any other ones out there, let me know. More than happy to sort of promote them. But have a go and see how you get on with it. But just practice using it. The worst thing you can do is watch this video and then not do anything about it for a couple of weeks. Because all that will happen is next time we do it, you go, we haven't taught us that, or I can't remember that, or worst thing is I can't do science. And it's not a case you can't do science, it's because you haven't been practicing. So just go through and practice doing some of those. And if you need more help with it, again, you know where I am. I'm always willing to help the people that ask. So we've gone through and we've looked at those. What I want to have a look at next then is specific heat capacity. I'm not going to touch any more of those. We've looked at energy transfers for the moment. There'll be energy transfers coming into these next few bits, but you're going to have to, it's not as implicit, I suppose, but we will talk about it as we go through. Specific heat capacity is one of the required practicals that you need to be able to talk about. Now, the definition for specific heat capacity, in fact, I'm going to type it because it'll be quicker for me. So it's the energy required to raise the temperature of 1 kilogram of a substance or material by 1 degree Celsius. So that's the definition that you need to know. Now, the formula itself is generally given to you in the exams. So what we're looking at, specific heat capacity, we're looking at the energy transferred. So I'm going to use this triangle to represent the change in energy, equals mass, because I've got mass over here, and the mass has to be in kilograms of a substance, multiplied by the specific heat capacity. Now, you don't need to know these. They would either give it to you, or it will be the purpose of the question for you to calculate. And I've got an example of that in a moment. Multiplied by the change in temperature. Now, they will often use that symbol there to represent change in temperature. Just because I don't want to confuse you too much at the moment, I'm just going to put temperature in degrees Celsius. So the change in energy equals the mass times the specific heat capacity multiplied by the change in temperature. So because it's energy, it's going to be in joules, kilograms, obviously degrees C, and this one is joules per kilogram degrees Celsius. So it's a bit of an unusual one there, but you can work out that actually if we multiply these together, what we get left with is joules. So as I said, you don't need to memorize that formula, but you do need to be able to explain what it represents, and you do need to be able to use it. But because it's got different parts to it, like the kinetic energy, it's actually one of the more complicated equations. But luckily in science, that's still easier than 90% of the equations that you're going to get in maths. Remember what I said the other day, is that the maths demand in the higher level papers of science shouldn't be any harder than a foundation maths paper. But the knowledge required for a foundation maths paper could be asked in a science paper. So that's the sort of level we're looking at the moment, but hopefully that should be easier than anything you get in maths. I think what a lot of people do is they look at this and they go, because it's science, it must be hard, therefore I'm finding it difficult. Rather than actually, if I work through, I write the formula down, scribe, substitute in, and then solve it, then actually I can do things like that. So let's have a quick look at an example for this one. Where the question number 1? That one there. So this is an example of a question. Again, I lifted these directly from AQA earlier. I really hope they don't mind me using their calculations. But at the end of the day, this is all practice for you guys, because you're going to be sitting their papers at the end. So metal worker quenches a steel rod by heating it to a temperature. None of that is important in the question, so I don't need to worry about this too much. What is important is I've got my temperature of 900 degrees Celsius before placing it in water. The mass, I need to know that. The final temperature of 50 degrees Celsius, because remember I need to know this temperature change, and the specific heat capacity. So now let me go through and solve the question for this one. They want me to calculate the energy that was transferred. Okay, so the change in energy is what they want me to work out, equals the mass times the specific heat capacity times the change in temperature. So the mass is 20 kilograms, specific heat capacity is 420. Change in temperature, going from 900 to 50, is 850 degrees Celsius. So if I type those into a calculator now, uh, 20 times 420 times 850 equals 7,140,000 joules. Now, I could convert that into kilojoules, depending on what the question asks me to do afterwards. So if I divided that by 1,000, that would give me 7,140 kilojoules. Or the question could ask me to put it in standard form. Remember I said we've got to get good at standard form, so that could be something else it asks me to do, in which case we'll be looking at 7.14 times 10 to the power of 6. Right, let's look at another example question on this. I've found these questions so they gradually get slightly harder as we work our way down. Remember, the context doesn't really matter with these. The examiners generally will try and put it into context, and because there's only a limited number of questions they can actually ask you, the questions will be weird and wonderful and random, and it doesn't make any difference what they're in. This is normally when students turn around and go, well, you didn't teach us about that. When actually it's the science behind it that's important. And I'm sure some days they just get bored and they just come up with the most random thing they can find out. Anyway, if we have a look at the information they've given us, same as we did before, the initial temperature is 25. It decreased the temperature to 20 degrees Celsius. So the can chiller decreased the temperature. So we've got a 5 degree Celsius change. The amount of energy transferred from the liquid, so that's our change in energy, and then the mass of the can was 0.33 kilograms. This time they want us to calculate the specific heat capacity. So let's go through, and I want you to be getting bored with doing the same thing over and over again. I want you to be looking at it going, but I can do this now. Why is he going over it again? Because it's that repetition which gets us really, really slick and good at this in the exams. So I'm going to write it out again. Change in energy equals the mass times the specific heat capacity times the change in temperature. My energy, it tells me, is 6930 joules. The mass is 0.33 kilograms. Multiplied by C, and I don't know C, but I know that my change in temperature was 5 degrees Celsius. So I need to be able to rearrange this. 6930. Now it's up to you how you do it. I would generally multiply 0.33 by 5 and then divide. But I'm not going to this time because I want to see, for you to see a different way. So 0.33 times 5 equals C. Now, the reason I haven't done it the other way for the moment is you need to remember bid mass. This is one of those times when most people will make mistakes on their final answer. So if I type this into the calculator, 6930 divided by 0.33 times 5, what I will get isn't the correct answer. Because what I'll get is 6930 divided by 0.33 equals multiplied by 5. Now, because it works out the division before it does the multiplication. So we need to be aware of that and either put brackets around this or do this part of the calculation first, which is what I'm going to do now. So 6930 divided by 0.33 times 5 equals 1.65. Now I'm going to get the correct answer for it. So if I go back, 6930 divided by 1.65. It's 4,200, which is the specific heat capacity of water. Joules per kilogram degrees C. Okay? Now, what that means, putting it into sort of words, giving it a numerical value, is that every kilogram of water would require 4,200 joules of energy to raise the temperature by 1 degree Celsius. So you can start thinking, actually, in the winter, when we're trying to heat up our houses, and if we've got a central heating system that relies on water, we're actually having to heat up a large amount of space, because what we want to do is heat up the water, so that energy then can be released into the room, so the boiler can carry on heating it. But every kilogram of water is 4,200 joules, just to raise the temperature by 1 degree Celsius. So actually, the more efficient we can make the house in terms of double glazing, in terms of cavity wall insulation, in terms of loft insulation, draft excluders, all of these little things means we have to actually transfer less energy because we need to heat the water up less, which is going to save us money in the long run. Okay, one more. And then I want to talk about the required practical with this one. And then I will let you guys enjoy the rest of your day. So, I haven't bothered putting all the previous question in. I haven't bothered putting the picture of a coffee machine in. Again, it's one of those things. We don't need to know it. And your job as students now and scientists in the future, however you want to look at it, anytime you look at something in a newspaper or you look at something in a book and you start questioning the information you get given, and bearing in mind everything you read in the newspaper you should question, because journalists' one job is to try and get a reaction out of you. So they all phrase things in whichever way they can. The Daily Mail is probably the worst one for it. But every time you ask a question about the information that you get told, you are being a scientist and you are doing science, okay? So what we're doing here is we're ignoring all the waffle, all the other bits and pieces that comes around it, and we're just taking the information. Here I have my change in temperature. And on an exam paper, I would be annotating the question exactly the same way as I'm doing it now. Or whichever way makes sense in your head. So that's going to equal 70 degrees Celsius. I'm going from 20 to 90. Now, this is a more tricky question. Okay, I have a power value here. And I haven't taught you about power yet. So we'll look at that in a moment. So power is the energy transferred divided by the time taken. Okay, so basically it's the rate that I'm transferring energy. And they've told me that, and that's in watts, that's in joules, that's in seconds. So this is a bit more of a complicated question, but you'll see the relevance of why I put this in a minute. So I've got the specific heat capacity here. So that's my value for C, and I've got a time. So if I was to go through and do what I did before, so let's have a quick look. We've got our change in energy equals my mass times my specific heat capacity times my change in temperature. Now, I don't know the mass. I do know the specific heat capacity. And I know the temperature change. But I've got two unknowns. And so I'm going to have to calculate one of these two. This is where the power comes in. So, 2.53 kilowatts. I don't like working in kilowatts because this needs it in watts. So, 2,530 watts. It tells me that I'm doing it for 14 seconds. So, let's put in my formula because as I've told you all the way through, we need to make sure that we scribe first. So, energy divided by time. If you want to rearrange it, that's absolutely fine. Energy transferred, which is that, equals power times time. So 2530 times 14 seconds equals, and this is going to be a big number. And that's the other thing that confuses students. They get a number that's really big and they go, I must have made a mistake. Probably not. I am transferring 35,420 joules of energy to heat up some coffee. Sounds perfectly reasonable to me. I'm going to put that value in there. Now I have a calculation that I can work with. What I need to do is rearrange this so I can work out the mass of the water. So, as I did before, oh, there's a 2 in there, divided by 4,200 times 70. Again, I'm going to work out this bit first because I want to make sure that I don't make any mistakes when I type this into the calculator, because it's going to make me cry if I make a mistake on the paper that I could have avoided by doing this properly. But even if I do, because I've shown on my working out, it's not a major issue. I'm only going to lose 1 mark. Just double check that. 4,200 multiplied by 70 is a big number again. But it's correct. 294,000. Okay? So let's divide these numbers and let's work out the mass of water. And then I'll stop doing calculations and I'll let your heads rest for a minute. Sigh of relief from some of you. Equals 0.12 kilograms. I tell you what, I'm really hoping that my cup of coffee weighs more than that. I would want a bigger cup from that one. But that's the calculations that go through. Again, I know this question. This question is worth 5 marks on the exam because there's so much math involved. I've got 2 formulae. I've got this one here. I've got this one here. I've had to pull information from the question and I've had a rearrangement to do as well. So that's a lot of work to do. But it's one of those things, if you look at the question and go, I can't do it, and don't write anything down, you're going to lose all 5 marks. If you start putting down things like this, where you're starting to substitute in, you maybe start doing one part of the calculation as much as you can. You might even do part of the rearrangement, but you don't get all the way there. You're going to be building marks all the way through. And at the end of the day, if we're looking at it and go, I can't get all of the way through this, getting some of the way means you will get some marks. And that's what we're trying to achieve. Now, I've just seen the time, so I'm not going to do the required practical now. I'm going to do that on Friday because I want to make sure that I can do it and I don't want to rush through. I want to leave you with those calculations. Go back through, slow me down if you can bear to hear my voice again, and break down and look at where I got the information from, what calculations I did, and how we got there. And again, you can work out things like this one. You can sort of make up the data. You can change the information in the question and have a go at reworking it to see what happens. You could do this particular one. Now that we know some of the answers for this one, you could turn around and say, how much energy would it do to make Mr. Weston a kilogram of coffee? Because that's what he really wants to be drinking, not 0.12. And you could plug that data in and work out the energy that you would have to provide to heat up that quantity of water. Yeah, Tanishka, no problems. I will sort out some practice questions and I'll drop them onto Google Classroom for you. Okay? Because it is one of those things and it is just practice. And don't be afraid of getting them wrong. Just play around with numbers. I think a lot of people, they look at this and because it looks difficult, they don't get all any way through. All I can say is if it's looking difficult, remember the 3 S's. Scribe, substitute, solve. Write out the formula that you're going to need to use. Then see what information you can find in the question that you can write underneath that question. If you get to that stage, I guarantee you'll start getting some marks from somewhere. But what a lot of people do is they go, I can't do this, and they don't write anything down, and that's where they lose the marks on it. So always write the formula down, even if you've got it written in the question, because a lot of the time, sometimes I'll give you the formula, write it down again, but write it down in a way that you can substitute information underneath it. Then once you've substituted it, then see if you can solve it. If there's 2 variables missing, you might need another equation somewhere. But a lot of the time you won't know that until you've written this down and actually substituted in. Okay? Right, I'll leave you with that. Hopefully I haven't hurt your head too much. But have a great day. And I will do another one of these on Friday for part 3. And then it'll be your half term. So take care. Any questions, put them in Google Classroom. And I'll hook out some practice questions on this for you. Have a great day. Take care.